Hello everybody and welcome to this XP Live webinar. My name is Nicole and I'm the marketing manager here at XP Solutions in our Portland, Oregon office. Today's topic is holistic urban 1D, 2D flood modeling. Today's presenter is John Howell. John has about 25 years experience in the modeling and simulation world. Prior to joining the XP team here, he worked with both Wallingford and Bentley software companies. Before that, he was involved with commercial software for computational fluid dynamics. Thank you everybody for joining us, and John, I'll let you take it away.
Hey, thanks very much, Nicole. Welcome everyone. Thanks for taking time out of your day to attend our webinar. I hope you find a lot of value here. So let's jump right into it. Today's presentation is about 1D, 2D modeling for urban flood events, and we can take a look at this picture that I popped up on the screen, and we can immediately see a lot of complexity there. So 2D modeling has been around for a while. We began offering it in 2004, but the capabilities around 2D modeling have matured, so the ways in which we use 2D models has progressed greatly. Recently, there's been a lot of buzz surrounding the release of HECRAS 2D, and I understand that. It's great. It's generating a lot of conversation at the conferences and trade shows that we go to, and we're seeing presentations about it, and it's free, so that attracts a lot of attention. The way we look at it is, the more attention on 2D modeling, the better, but like any task, we also feel that some tools may do a better job in different situations. For urban flood modeling, we take into consideration a whole set of factors that can impact a flooding situation in an urban setting. Factors that, if ignored, can impede our ability to reduce risk, which is why we're doing this in the first place. So today we're going to talk about the complexity of urban flood modeling. For example, if we take a look at the model results you see on the screen now, we actually have 1D channel. You can actually see the 1D channel on the right-hand side of the screen there feeding into the urban area. We also have a stormwater network, a 1D stormwater network that's being modeled, which represents storage, and both of those interact dynamically with the 2D Overland flow model. And as you can imagine, we get some very complex flow regimes out of this, as you can see by the graphic. So when we model these types of events, we want that 1D channel model, we want the underground storage, we want the 2D Overland flow, all working together to deliver an accurate picture of what's happening in the urban environment. So kind of the order of battle today, we're going to talk about topography, your digital terrain, and the way that we use that in 1D, 2D urban flood modeling. We'll discuss storage. So storage to us can represent storage in a 1D channel. It can represent storage in a stormwater or combined system, 1D model. Storage can also exist on the surface itself, and that's one of the beauties of 2D modeling, is can actually accurately capture what happens to that flow as it escapes out onto the terrain. So we have storage in all three of those model elements. We'll talk about 2D hydrology and a little bit about the differences in 1D and 2D hydrology and some of the capabilities that we have in 2D that we didn't really have in 1D. Then we'll talk about urban hydrodynamics. So there's a lot that goes into describing the urban environment. In our 2D model, or in all 2D models, you have to generate a computational grid that accurately describes the 2D surface. Of course, you use the 2D surface to do that. But the grid generation, some of the other elements necessary to describe the urban hydrodynamics, we'll go over a few of those. And then we'll talk about some of the dynamic things that we can do with 2D models. 2D models, because we're dealing with elevation, have the ability to include a lot of dynamic elements if we have the right tools to manipulate those elevations. So we'll cover what some of those dynamic factors are. And then we'll discuss results and what you can do with some of the 2D results that's really creative and is very compelling. So let's start the first poll. We're going to try to take the temperature of the group and see how much modeling experience we've got amongst the attendees.
Yeah, great. So basically we'd like to know, for folks who are joining us today, what types of modeling experience do you have? And you can select one or many of the options available. So do you have mostly experience with basic hydrologic or hydraulic modeling, Do you get into more complex drainage studies? Is NFIP flood mapping something that you have a lot of experience with, or rural and river flood modeling? Or do you do a lot of urban flood modeling, which is a lot of what we're going to be talking about today? So it looks like most folks here have experience with basic hydrologic or hydraulic modeling. There's a lot of folks who've done complex drainage studies and urban flood modeling, which is great. And then a few folks who've done some river mapping and the NFIP flood mapping. So it's good to know. It's very interesting.
Great. So moving along, we're going to talk a little bit about surface data. So you guys probably, most of you recognize the graphic on the left if you've done any catchment modeling, and you probably recognize the graphic on the right too. But of course, we can tell just from visual inspection that these are two very different representations of terrain. The 1D catchment model is the way we're all accustomed to doing it. Well, I shouldn't say we all are accustomed to it. There's probably some people in the audience that are young enough that they've never modeled in 1D. But for the rest of us, we've done some of this. Today, accurate terrain data has become widely available. There are a lot of reasons to have accurate terrain data, whether we're doing 1D or 2D modeling. A good 2D surface representation allows us to manipulate 1D elements. If we're just doing 1D modeling, I may want to lower some node inverts relative to the surface or tie the node spill crest to the surface. And so having that digital terrain as part of any model is important, but of course it's essential when we're talking about 2D modeling. In the past, we used these 1D catchments basically as an approximation of the terrain, for lack of a better word. It makes a fair amount of assumptions. So we're going to define an area, we're going to define a slope, and that's got to be an approximation. Can you imagine trying to actually use this approach on the left to describe this complex terrain on the right? We'd have literally probably thousands of catchments, as if we wanted to consider these slight areas of depression here or these major changes in terrain over there. But it served its purpose. It allowed us to basically route runoff to a node over an area, and then we could apply certain models to that catchment. We could apply infiltration models, evaporation models. So there was some flexibility there in terms of how we wanted to treat the runoff to the node. But there's some limitations as well. So let's say part of a catchment crossed an urban area, kind of like this one does here, catchment 8, and part of it is sitting in a field. Well, I've got two different types of infiltration probably going on there. The impervious pavement is not going to be the same as the more pervious soil. So how do I describe that in the catchment? So I've got to make a lot of assumptions to really model that in 1D. In 2D, the delineation of the terrain is precise. We just use the terrain model, right? And in addition, we can use additional data to really dial in and give an accurate representation of the 2D surface. If I have a shapefile that contains street shapes, and I've got another shapefile that contains pasture land and another one that contains building polygons and so on and so forth, I can assign infiltration models and evaporation models or what have you based on the geographic location that's represented in the shapefile. So I can be very precise as to where I'm going to have impervious soil. It's where my streets are, right, relative to a residential yard or a pasture. So modeling in 2D just allows a much greater level of accuracy based on a lot of the ways that we can describe the terrain. And of course, it totally removes the need for catchment delineation, and I know for those of you that have done a lot of that, it can be fairly tedious. So let's talk about 1D storage. And if you've used SWIM or any of the other modeling packages and you've modeled in 1D, if we're modeling a stormwater network and we've got overflow at a node, the SWIM engine allows us to actually ignore that overflow. It then becomes lost to the model, right? So we don't account for the flow anymore. It also allows you to define storage at a node. SWIM will allow you to define basically what is an infinite column that rises above the node, and then the surcharge that resides in that column can return to the network once the network regains the capacity to return it to the network. XP Swim goes a step further. We'll allow you to define how the overflow can be stored. You know, you can as a constant depth, or as a function, or you can use a stepwise linear function to prescribe the shape and the volume of the storage of the node. So you can mimic, for example, a detention pond. So there's a little bit of flexibility on how we can store things at the 1D node. But the reality is that if we were driving around in a car and we drove by a manhole, there's not going to be an infinite column sitting above the manhole ready to take the overflow, or a kind of a saucer-shaped basin ready to catch that overflow. That overflow actually spills out and it goes onto the ground, which we represent by the 2D surface. And what happens when it hits the ground? Does it just sit there and pool up? Well, maybe if the terrain is bowl-shaped right where the node is, the water would stand there and pool up. But in reality, it hits the ground, and then dynamic things start happening. And that's one of the beauties of 2D modeling, is that we can actually start accurately describing what happens to the overflow when it comes out of the node. You know, this is what happens in an urban area when water comes out of the 1D network. It impacts, it pools up based on the surface elevation. It interacts with the 2D urban environment around it, sloshing up against the doors, maybe seeping in and flooding the basement, or running down the street and into another manhole at a lower elevation if capacity dictates, and so forth. So it's very dynamic, the actual urban environment, and really not much like the 1D representations that we used to have that would just like store the water in place. Now, we did have ways in 1D to try to capture some of that dynamic activity. You know, we could implement a dual drainage model where we would actually define an overland flow path, and then we'd define, a cross section for that overland flow path, and therefore define the capacity for that overland flow, and basically let it, trickle down maybe a street, right? And re-enter the system if we had capacity at the next manhole. But again, this is incredibly tedious to do, and there are huge limitations to this. I mean, mostly this was used for modeling flow in streets between surcharging manholes. It's not realistic, when high flood conditions exist and flooding extends beyond the streets. Once it overbanks the curb, or flows into a ditch that diverts away from the street, then we've lost any way to accurately capture what happens to that flow. Whereas the graphic on the right kind of is representative of what happens with 2D drainage. So the 1D model is linked to the 2D model. In this case, our 1D model is this channel over on the left, and we can see this pasture land here, and the channel is overflowing kind of into the pasture land and up against probably this berm area that's beside the road. It finally overbanks the road, and then it impacts our little town or our village here. And what happens when that flow impacts the town or village? Well, it starts flowing between our houses, and it flows into our streets, and it might flow down multiple streets, and it might re-enter at various places in the storage network. It becomes very complex. So a much more accurate representation is available in 2D than trying to model this with the older techniques. And this graphic just kind of illustrates that. This was a large XP Swim 2D model that was done, and this is a large urban area, but look at the different pathways that the overland flow is taking. There are literally hundreds of them. There's a 1D stormwater network underneath this this representation is capturing some of that flow, but imagine the complexity of what's going on here. If you try to model this in 1D, can you imagine the number of different mechanisms you'd have to put into the model to even try to get close to this? Whereas with the 2D model, we can consider the urban terrain, right? We can consider the buildings. We can consider the streets. They can be part of the topography. So a much more accurate representation with much less work is available when we model in 2D. So let's talk a little bit about 1D and 2D model integration. And I put this graphic in. It's kind of over the top, but this was actually the World Trade Center construction site when Superstorm Sandy hit. But as you can imagine, if you've ever been to Lower Manhattan, I mean, it's chock full of tall buildings, so there's really no surface area other than the streets. So once the water rose to the point where it was flooding in the streets, really strange things start to happen. So there are depressed storage areas, which will be represented by this construction site. There are basements of buildings, there are subway tunnels, and all of that water's got to go somewhere. This type of dynamism is what we try to capture in 1D, 2D modeling. So what we got to have for 1D, 2D modeling are 2D is a 2D overland flow model that's linked to either a 1D channel model or a 1D network model. The 2D equations that we use, I don't want to go into too much detail here because you could do a whole presentation just on the right equations that need to be used, but we solve the shallow water equations for 2D, and we include the terms for bottom slope, friction, acceleration, and pressure. So we solve the full set of equations. These equations have been validated against physical models, and they've been proven to be an excellent characterization of overland flow. We combine the 2D equations with, combine the 2D equations and link them dynamically to our 1D models. And our 1D channel model and our 1D stormwater model use the full St. Venant's equations with all the terms. So then we have to link those in time. So at each time step, our 1D channel model, our 1D stormwater model, our 2D model can be exchanging flow with each other based on, the things we've talked about already. The 2D terrain, is there capacity in the network? Is my 2D model returning flow to the 1D model? Or is my 1D model still surcharging and delivering flow to the 2D terrain? These have to be linked in time, so at each time step, you have to have the ability to accurately exchange flow between the three different types of models that I just described. And we have tools to do this. We do this using basically some 1D, 2D interfaces that the user defines in the software. And this process, it's a little bit complex, but we've got to accurately capture these interfaces if we want to give an accurate representation of what happens when the water spills out onto the 2D terrain. So hydrology, as we mentioned when we looked at the catchment model, we have a lot of ways in the past that we've modeled hydrology, in 1D. And one of the things we used typically was a design storm. And on the left, you'll see a typical design storm. This is a Chicago storm hyetograph. In reality, what do rainfall events look like that cause flooding? They're going to look more like this. In this case, we've got a storm of about 3 hours duration, and it's got basically 2 peaks in it. And this is actually measured data from an event that caused flooding. And if we have this type of data, again, we want to use this. This is more accurate. This is more representative of the real world, and we want to always in 2D modeling strive to capture that realism. And why is it important? Well, it's important because of some of the things we've talked about already. I might have a pretty high peak, a pretty high onset of a fair amount of flow that tapers off, and my network may be able to handle it. Maybe I've got enough storage in my stormwater network that it doesn't overflow or doesn't overflow much, and my creek is able to accept some of the flow, and things start to taper down, and then my second event hits. Well, the ground has already reached saturation point, and the channel is almost full, and the stormwater network's almost full, and even though this is a lesser peak, the second time around it can cause a tremendous amount of flooding. So it's always a good idea if we have good data, especially data that's been used or gathered from a previous flood event, that we capture that and try to use that in our 2D models. We can also capture flow in 2D by raining directly on the grid. In the 1D catchment model, we'll have an event and we route the flow, right, over the catchment. And we've discussed some of the limitations of that. The great part about 2D modeling is that we can rain directly on the grid. Well, what do I mean by directly on the grid? So in 2D modeling, as I mentioned before, we're going to create a computational mesh that mimics the terrain data that we have, so it's overlaid onto the terrain data. So at any point on the terrain, I've got a computational cell of a certain size, and that cell is going to be surrounded by adjacent cells. Each cell has an elevation value, right? So instead of using a runoff model that collects things at a node, we're going to let the flow fall directly on the cell, and then the rate of rainfall and the elevation of the cells adjacent to the cell in consideration are going to be computed, and that's going to determine which direction the flow goes, which adjacent cell is going to receive the flow. So that's a much more accurate representation, again, of what happens when rain actually falls on the ground. One of the things that we also want to talk about today are some of the factors that go into 2D hydrodynamics, right? So in the old way of doing hydrologic modeling, we had the catchment basin. We just talked about, now we have terrain, and we've got a computational mesh that we're going to overlay onto that terrain. One of the things that's important in that consideration is how we're going to discretize the grid, or how fine or how sparse can we make the computational grid. Well, the engineer's objective should always be to use the least amount of cells I can to accurately describe the flow characteristics. So in the graphic on the left, you can see that a 20-meter cell leaves us with a pretty crude representation of what's going on in the model. When 10-meter cells were used, we actually see different flow patterns here. And when we went all the way down to 5-meter cells, we're actually capturing areas of recirculation. We're capturing the flow between these two buildings here, right? Because now we have a fine enough grid that we have a flow path established between those two buildings, which is what we'd see in the real world. So as engineers, we have to kind of determine what's going on in the model and what's a reasonable cell size. This is an important trade-off simply because smaller cell sizes mean longer run times. It's a dilemma that we're stuck with. Smaller cell sizes can mean much greater accuracy. So we have to find that balance between what's a reasonable cell size and what is accurately describing the flow in the 2D model. And just as a rule of thumb, so having the cell size increases the runtime by a factor of 4, right? Why? Because it increases the number of grid cells by a factor of 4. So, little rule of thumb there. We do have the advantage today, though, of having modern hardware to run this stuff on. In a previous incarnation, I was working with a group that developed commercial computational fluid dynamics software, and we ran this stuff on Cray supercomputers, and it could run for days. And I think my iPad probably has about as much processing as some of those original processing power as some of the original Cray computers. We also can use tools. The software has tools to optimize our grid sizes and make the best use of the computational resources that we have. So in this particular graphic, this is the same graphic that you saw earlier with a little bit different thematic mapping on it. I've got my channel, my 1D channel coming into the village, and as you can see, I'm getting some flow over the bank into this pasture area, right? And then it's impacting this urban area right here. So which is of more interest to me, flow across a pasture or what happens when it gets into a populated area? Well, naturally, once it flows into the populated area, it poses more risk. And I might want to determine, well, what happens when the flow goes between two buildings? What do those velocity profiles look like? How risky is it to be in that part of town during that event? So I'm going to want to discretize the grid at a much higher level of granularity in this area of the village, which I hope you can see. The background image is a little bit washed out there. So one of the tools that we give you in XP Swim is multi-domain model. Now you can see the little village area, and this is the area where I saw some flow down the streets and flow between the buildings. I can actually create a more finely gridded mesh that's a subset of the larger mesh to capture the characteristics of the flow in that area much more accurately. That mesh is then embedded inside the more coarse mesh. So now we're going to have flow through the channel, over banking, and entering the village. And once it enters the village, we've got the spine grid, which is going to give us a lot greater level of detail in terms of looking at what's actually happening. It will allow us to see the flow through the buildings and so forth. Along with that, as flow enters this more finely gridded mesh, I might want to crank the time step down. So we have tools for that, for treating the time step differently between this more sparse mesh and the fine mesh in the center. Why is that important? Well, if the flow's going fast enough, right, and the flow is more unstable, we actually need the ability to crank the time step down just to keep the model stable in some instances. But all those things combine to give us a very high fidelity look at what's going on in this area of interest in the village. Next, I want to talk about buildings in the floodplain. So we've got a couple of interesting graphics here, and we can see where in the first graphic, channel, the overflow from the channel is kind of overlaid onto this urban area down here in the bottom right. And when I asked the question, well, what kind of treatment did the buildings receive, and was storage considered? The answer was, of course, no. Whereas the graphic on the right, we've accurately represented the buildings, and we've accurately represented the underground storage. We've accurately represented the urban environment, and you can see the difference in the pattern, right? Why model buildings at all? Well, consider this photo. So what percentage of the terrain is occupied by buildings? It's over 50%, right? So if we're going to model flooding in an urban environment, we have to have ways to treat the urban topography. And we should be looking for ways to treat that topography so that it gives us meaningful and accurate results, right? So unless you have the capabilities for considering these buildings in detail, especially for environments like this, I don't think you really have any confidence in the results of the model. So for urban flood modeling, we have to have robust ways of treating buildings in the floodplain. In this graphic, we can see we've got a little cul-de-sac here, and I've got half of one house flooded, the other half appears not to be flooded. This house over here isn't flooded at all. Is there 20 feet of difference between these two homes? My street's totally inundated here. The cul-de-sac over here is inundated, and this house is totally inundated, but the one next to it, which appears to be just, from visual inspection at this roughly the same level, is covered by water. Well, in reality, we all know that this is basically a JPEG file that's been propped up behind what's basically a surface model. So this is a floodplain elevation, and we've mapped in a JPEG file in the background. Because in reality, we would see flow, those flows would have increasing velocities. Those velocities are important for us to understand and how they increase and decrease over time. So we're going to have the next poll, and we're going to ask those of you who do 2D models, how do you treat your buildings? So Nicole, over to you.
Thanks, John. Pretty sure everybody can read what's on the screen, but so how do you typically represent buildings in your 2D models? Very common thing to do is to use a Manning's roughness for each building. You can also use an inactive area to block it from flow. Another option is you can use a fill area where water can enter at a certain depth. And then lastly, there's a layered approach where you can have a loss coefficient per layer to simulate what might happen in a structure. So if everybody could select one of those options, which is most typical for you. It looks like the inactive area is the most commonly common way folks represent buildings in their 2D models, with Manning's roughness a close second. All right, thank you so much. That was very interesting to find out.
Good. That's not surprising. That's a very valid. That's a valid approach. As all of these approaches are valid, we're going to talk about 4 ways to model buildings, and all of them have validity. And this is where I think engineering judgment comes into play. So if we use a very high Manning's N value, if it's at some point we might get flow over the building profile, and in most cases we're just going to have a shape file with polygons in it. We're going to put an extremely high Manning's roughness on it. At some point water might flow over that representation of a building. There's really not a building there at all. There's no elevation, right? But for certain types of modeling, this is totally acceptable. What if we had a very shallow flood and it was very fast moving, right? And it's probably not going to go into any of the buildings anyway, just a couple of inches. Manning's roughness would be fine. In other situations, we might want to use different treatments. One of the treatments that we offer in XP Swim is the inactive area, which a lot of you are using. And for those of you that use it, you know that basically the polygon boundary is basically an infinite vertical wall that extends up into the sky. and water is allowed to pond up against the polygon and not enter it, and that doesn't change over the course of the model, regardless of what's happening in the model. And it's a great way to represent, I think, fast-moving flood events where you're not going to have a lot of inflow into a building, or you're unlikely to, or at least modeling that would be more effort than it's worth. It's a great representation of how the flow is going to act between two buildings, and in a fast-moving event, it's in a very valid way. But it's totally up to your engineering judgment. Each of us, when we're modeling, has to take into account all of the components of the model and make the decision on what treatment to use. The fill area is something we offer in XP Swim, and with the fill area, water can pond up against the building and not enter the building until it reaches a depth that is more than a fill depth that the user prescribes, right? So if you're in a residential area, maybe the first typical point of entry into an urban structure is the front door or the back door, which has a lower elevation than my windowsill. But I might make the assumption that, well, 90% of those doors are closed, or 95% are closed, and the water's not going to seep in very fast. So I'm going to make the fill depth the first windowsill, which might be, 5 feet above the surface level or what have you. Anyway, all of these are approximations of what's happening during a flood event. Again, it's up to us to use our engineering judgment to try to determine what is the most realistic representation of what's actually going to happen. And sometimes we're limited in the tools that we have. These tools, again, are approximations, but they do allow us to have some degree of flexibility in how we want to treat the buildings. The most complex way that we offer out of the box to treat a building is the layered approach. So we're going to have a blockage factor per layer and a loss coefficient layer that basically allows us to fill the building with water over time. And again, our engineering judgment comes into play as to how I want that to occur. Is how fast moving a flood event is this? Is it a situation where the river is overflowing and it's just a slow rise of water and there's very little dynamic flow? That might be a good time to use this particular approach. Or you could also use this approach in a fast-moving storm as well. But again, the layers that are prescribed and the rate at which those layers fill up requires our engineering judgment. Tony Cooch even told me that we have additional tools in XP Swim that we can use. We can create areas of depression storage. So we can basically take the building polygon layer and we can punch a hole 10 feet down into the earth below the surface, and that depression storage is storage that can fill up with water. And then we can take dynamic elevation shapes, which we're going to talk about here in just a little bit, and create a boundary around that storage area. And this would be a great way to mimic basement flooding in urban areas. We can say once the water gets to 6 feet above the surface, it's going to fill the entire basement plus the 6 feet of the first story, right? So we have other tools in XP Swim that allow us to be creative. They're not really out-of-the-box capabilities. They require that we be a little creative in how we use XP Swim. Again, the idea is to accurately capture as much as possible what's happening in the flood event. There are a lot of dynamic things going on in a 1D, 2D urban flood model. In both the 1D and the 2D model, we can have changing boundary conditions over time. The flow into my 1D channel may greatly ramp up and then recede. Things that are going on in my 1D storage network can be changing based on real-time controls and pumps and things like that. The flow regimes themselves can change. The rainfall event changes over time. How these different models interact with each other is going to change over time. And the urban terrain must be considered in all of that. One of the ways that we do that is with dynamic 1D elements. Most of you are familiar with these. So if I'm modeling a stormwater network, I might have real-time controls to turn on pumps or to blow up an inflatable weir or what have you. So there are all kinds of dynamic things happening in 1D models. Likewise, when we are treating the 2D surface, we need to be able to dynamically work with the terrain data and what's going on with the terrain, because that can change over time as well. One of the ways we do this beyond just things like head and flow boundaries is with dynamic elevation shapes. So we're given a digital terrain model and we read that into our modeling platform and we create a surface, and we create surface elevations, and that allows us to create a computational mesh with elevations at each cell, right? And then we run the model, and the results are delivered based on that computational mesh. What we can also do is change the elevation of any of those cells at a given time. These are called dynamic elevation shapes in XP Swim. The little graphic that I have here is actually a retaining wall that was built around a recreational area. I can see a soccer field there, and it looks like just a big open field here. I've got a 1D channel here that's overbanking, right? So we build a retaining wall around, in this simple example, this recreational area. And this green blob you see right here is a feature of XP Swim called a trigger point. And we might want to say that this dynamic elevation, in this case, basically a one-dimensional wall, this wall is going to keep flow out of this area until this trigger point determines that for some reason this dynamic elevation shape changes. And in this case, we're going to have a breach of the wall right here. We've defined this breach as something that happens when this trigger point is reached. This trigger point can be any modeling result can be a trigger point. So it can be a velocity at this node. It could be a depth at the node. It could be a combination of velocity and depth at a given point. And that will cause the trigger point to change the shape of this retaining wall, and then we see the flow going in the soccer field. But this is just one example. Think of, there are a lot of different examples I can give. We allow you to use both polylines and polygons as dynamic elevation shapes, so you're not limited to just lines. The fact that we can use polygons as dynamic elevation shapes, and that we can change the elevation of elements of that polygon dynamically, allows us to create berms, we can create levees, we can actually lower the elevation based on an event. We can simulate depression storage by taking a dynamic elevation shape and basically just drawing a detention pond very rapidly to mitigate overflow, to test how that might help us in a very rapid fashion. It's one way to very rapidly implement mitigation structures in 2D modeling, but it really requires the creativity of the modeler to determine how to use the dynamic elevation shapes. The possibilities are kind of endless, because we can trigger the change in these dynamic elevation shapes based on the simulation time, based on a water elevation or water elevation difference, and basically we can lower or raise the vertex elevations of these polygons based on any criteria, including time in the model. So there's really an unlimited way you can work with these. It's more dependent on your creativity and what the model calls for. And this is just a graphic of the interface of the 2D dynamic elevation shape menu. But you can see here that it gives you a lot of flexibility. It can be a water level that triggers the dynamic elevation shape, a water level difference. It allows me to lower or raise current elevations, change all elevations, et cetera, et cetera. A tremendous amount of flexibility. Finally, I want to talk about results. So I'll date myself a little bit here. Probably the graphic on the right was the state of the art when I started working. I came out of school and went to work for Lockheed Missile and Space, and we had these giant plotters. We had a room full of them. And this is about what we get out of them. So when I started out, the image on the left, the log file, and the image on the right were about the state of the art. That's what we had to work with and when we analyzed models. And things have changed over time. We still can get a lot of value out of, believe it or not, the 1D logs that come out of XP Swim. They contain a lot of metadata that's valuable, ways to quickly interrogate the model to see where we might have problems, but it's not nearly as dynamic as the animations that we now have. We have animated 1D results. We have a section view and a long section view that can allow you to look at a stretch of pipe. We animate it and show you what happens over time. So we have dynamic ways of viewing 1D data and have had it for some time. With 2D, it's a whole new world. So 2D data allows us to almost an infinite variety of ways to present data, to look at data, to share data with stakeholders, and so forth. All of our model outputs, our velocities, our depths, all of these are correlated in space and time. So as you work through a model, and in XP Swim we have a little slider bar at the bottom. So once you've solved a model, you can use the slider bar to go to any point in time during that solution run, right? And we can look and thematically map any of the information that's an output of the model, whether it's, like I said, velocity vectors, depth, flow, what have you. We can also immediately export this data. You can stop the model at any time and right-click on this image and export this as a shapefile. And we have full control over the thematic rendering of that shapefile. And it's just a matter of a few buttons, and I can export it as a map info file, a shapefile, what have you. And I think that's important because a lot of our stakeholders aren't engineers. A lot of people that end up needing the outputs of modeling are not. They're stakeholders that might sit on the city council. They might be somebody that's involved in flood planning. It might be an emergency responder, right? So getting this visualized data into their hands can be very meaningful, and it gives us a lot of creativity on how we want to present results as well. Our animator is built into the platform, and it's you can also take our models and encrypt them and export them and allow somebody to view it, any of the results with XP Viewer, which is a free tool. So it's a great way to get dynamic information out to your stakeholders, whether they are modelers or not, at a very low cost. There's some other very creative things we can do with the model data. We can combine the data, and this can be very powerful. So we can look at values. We can combine scalars to come up with new values that give us a time to inundation at a certain point, or the duration of an inundation, or the time to peak, or in this case a risk value. Velocity times depth is a popular way to consider risk, and as we talked about earlier, the whole point of urban 2D flood modeling is to quantify the risk. We even give you some specialized tools to work with some of this data. In XP Swim we now have an evacuation route planner, and it allows you to define what is inundated, what depth means inundation. And I can have in this little example here, you'll see that in this case we defined 1 meter as the cutoff for pedestrian evacuation, 1.5 is the cutoff for vehicle evacuation, and 3 as the value for emergency vehicle evacuation. And we give you a special tool that allows you to lay down a 2D polyline, and then the route cutoff values are user defined. And routes can be analyzed for cutoff by, again, any of the scalars that we want to use. But this is an especially useful tool to get model results out to people that can use it during flood events, like first responders, police, and people that are involved in emergency response in any way. And lastly, I want to talk just a little bit about animation. I'm going to run this while I talk about it. Again, our animator is built into the platform. Doesn't require any additional file manipulation or file reads. You have full control of the display and thematics, and full control of the time series output. I think sometimes we underemphasize how useful this can be. In our animator, we output an ADI file, which everybody can pretty much play on their desktop. But again, this is a great way to get very compelling information packaged in a way that any stakeholder can understand it, and it's all part of the software. So as we're working with 2D flood models in urban environments, this becomes important, right? Because they're so complex, they're not easily understood by looking at tabular data, and I think we have to have excellent ways to represent the data. So just to kind of sum it up, we talked today about some different aspects of 1D, 2D modeling. I think the important ones were how 2D is different in the way we treat storage, how we treat hydrology, and then how we link up the different types of models that we're running, 1D and 2D, so that they all run together and they're linked in time and they're exchanging with each other in a realistic fashion to produce realistic results. And again, the reason that we want to capture as much realism and accuracy as we can is we want to quantify the risk of urban flood modeling. The urban areas are where our people are, it's where our property is, or most of it, and therefore it's where most of the risk is, and we want to capture that in as high a detail as possible. And with that, that kind of ends my presentation for today, and I'll turn it, Nicole, back over to you.
Thanks, John. As you can see in the slide that's available right now for everybody, we do have a couple other resources that are available if you would like to delve into our 2D information on your own. We did a webinar, I think a year or so ago, that was presented by a user of our software, and it was a model of Josephine County, Oregon, and it was pretty interesting because there was a lot of interaction between the 1D portion of the model, which were irrigation channels and I think a river, as well as the overland flow. And it was a detailed discussion of the 1D, 2D interaction across the entire study. And I believe one of the things they found was that if you followed a single drop of water, it would go in and out of the, it would go between the 1D, 2D parts of the model over 6 times. So it was a representation of how much interaction really there is between a 1D system and the 2D overland flow. So that was a very interesting study. If you'd like to look at that video, the link is there, xps.link/Josephine. I'd write that down and go look that up. It's pretty interesting. We also did a 2D modeling series last year that was presented by the author of our 2D engine. It was a 3-part series, and the titles of them are there. We did one on cell sizes, what cell sizes are appropriate, and a lot more to that. Structures in a floodplain, and of course direct rainfall, the hydrology part of the 2D. So if you're interested in that series, that's available at the xps.link/2D series. I think that's about all. If you have any questions, we're happy to help. You can always email John directly at john.howell@xpsolutions.com if you'd like to start a conversation directly with him. Otherwise, you're welcome to write to amsales@xpsolutions.com or ameducation. We'll get it both ways. Thank you so much, folks. Have a wonderful day. Thank you for joining us.
Yes, thanks for your time, everybody.